That last recording ended because I accidentally rotated my tablet too much and it changed the display settings. Hopefully this is the last video that I have to make. I'm sorry that it keeps cutting it off. But I think the last thing I said, right, was that, you know, just like when we were doing the anionic conditions, okay, or sort of the basic anionic conditions or the neutral conditions, it always is going to behave like an SN2 pathway, and the nucleophile is going to attack the less substituted part of the epoxide, right? So, for example, if I have a non-symmetric epoxide, okay, with an unsubstituted part and a more substituted part, right? As long as I'm in neutral or anionic conditions, it's always gonna, the nucleophile is always gonna go on the less substituted part, right? So for instance, when I added NH3, when I added ammonia, and again, I should put in, I keep forgetting to put in the stereochemistry. When I put in the stereochemistry, okay, right, then I saw that I was able to get this thing, okay, right. Right, when I put in sodium hydroxide, we saw that I was able to get this thing. Okay. And hopefully you guys can sort of see like the general pattern. It doesn't really matter. You can do this with a ton of nucleophiles, okay? So let's see. So instead of reacting this with like sodium hydroxide, you could react this with, if you remember what my favorite electrophile, or sorry, my favorite nucleophile ever is, you can react this with like sodium cyanide. Okay, so again, sodium cyanide is, it's anionic, so this is going to attack the less substituted part, just like a normal SN2 reaction would. So it's going to go there, that's going to go there. And then again, you're going to do this in some kind of solvent, probably water, something like that, so that this O- can take a proton from somewhere. Alright. And actually, you don't want to generate OH- before the cyanide, all of the cyanide, has had a chance to react. And so you're probably going to want to do step 1 and step 2, okay? But that'll be enough. So that in the end, you can get a CN there, right? Okay. Alright, so we have that. Alright, and again, the world here is your oyster. So there's a lot of nucleophiles that you can think about, you know, reacting with an epoxide in this way, right? If you don't want to use something like CN-, you know, another really common anionic nucleophile that you can use is a Grignard, right? So let's say I want to react this with phenyl Grignard. Or, yeah, phenyl Grignard. So that guy, right? So step 1, that. Step 2, water, right? So let's do this mechanism really quick. Right. Again, Grignards are neutral. They technically, you know, they react as if they were anionic, but they're neutral species. This is going to react in the exact same way. It's going to do an SN2 based thing. Okay, so we already know that when you see something like this, the best way to think about this is that it's going to do essentially the same kind of chemistry that this imaginary species would do, okay? So it's not equal to, right? Notice that I drew like a similar to sign, not an equal to sign. So these two species are not equal to one another, but it's going to behave the exact same way, all right? So what's going to happen is that the sigma bond is the actual nucleophilic species, all right? Oh, what the fuck? Yeah, I don't know why I did that. All right, sorry, my bad. Sigma bond is going to attack there. That's going to go up there. All right, and that gets me to... Oops, sorry, not OH, not yet. Anyway. All right. So that gets me to there. Whenever you're doing a mechanism with Grignard reagents, by the way, obviously you'll notice, right, that the MGBR is kind of now just MGBR plus, and it's kind of just floating around. You don't really need to worry about, what the MGBR does. The MGBR is non-reactive. It's a very, very non-reactive cation, so it doesn't really do any chemistry that we would actually be interested in. Okay. In fact, that's why Grignard reagents are so useful. The MGBR doesn't cause any kind of weird side reactions. But anyway, right, we get this, and then we throw in the water, which allows us to get rid of that negative charge on the oxygen. And so you can add Grignard reagents to epoxides. And it gets even better, because not only can you add Grignard reagents to epoxides, you can also add hydride reagents to epoxides. Now, you can't add every hydride reagent to an epoxide, so it turns out sodium borohydride is not a strong enough nucleophile, but you can do this with lithium aluminum hydride, alright? So again, make sure in step 2 you're throwing in something to get rid of that negative charge on the oxygen, okay? And again, right, we talked about this a little bit. If you ever see LiAlH4, I kind of want you to think about it as just H-. It's not technically H-, but it's going to behave in the same way. Okay, the reality is that it's actually the sigma bond. So the aluminum hydrogen sigma orbital is the nucleophile. So this right here is the actual nucleophile. But the mechanism is the same as if it were just H-, okay? And you can imagine, right, it's going to do the exact same chemistry that we've been talking about this whole time. So I have an epoxide, all right? I have nucleophile attacks the less substituted electrophile, which causes the leaving group to leave, right? And then that's going to get me to here. Alright, and then this is just an implied hydrogen, so I'm not even going to draw it. And then in step 2, I put in my water, yada yada yada. Bam, bam. And it's a way for me to get just one alcohol now. Alright. Okay. I'm trying to think of like literally every single nucleophile that I can think of for you guys. The only other one that I can think of, maybe that I haven't done yet, for the neutral and or basic conditions, is you can actually have so alkyne anions are really good nucleophiles. So that would be like a carbon, like a terminal alkyne. Okay, so something like that. Okay. And again, I'm going to do the mechanism for you just so you guys can get the handle of it. But hopefully at this point you guys are getting really good at the mechanism. It's the same mechanism for every single case. Obviously the products are different, but the mechanism is exactly the same. So again, you have a really, really strong anionic nucleophile. Therefore, it's going to do SN2 based chemistry here. It's going to go there, that's going to go there. And that's going to get me to here. So that gets me to there, and then again in my second step, I just need something that has a proton on it that I can deprotonate to quench that O minus. So that my final product looks like this. Alright. Alright. So hopefully you guys thought that wasn't super difficult. Alright. And that was the neutral and or anionic and or basic conditions. So now let's talk about when you are under cationic or acidic conditions. So the mechanism is going to be a little bit different, and the regiochemistry is going to be different, all right? And we're going to talk about that. So before, right, when we were looking at this, I don't want it to freeze on me again. So before, when we had this epoxide, okay, we said that if you react this with sodium hydroxide and water, right, what would happen, and you get, well, I shouldn't do sodium hydroxide and water. Let me do, well, I guess, yeah, whatever. So the sodium hydroxide ends up attacking this carbon right here, right? And you get this species, okay? But what would happen, how would the mechanism change if instead of sodium hydroxide in water, you did H2SO4 in water? Right? How would that actually affect it? So we know that epoxides are nucleophilic, right? We've talked about that. So we know that if you're under acidic conditions, the first thing that's going to happen is you're actually just going to protonate that epoxide. Okay. So once you've protonated that epoxide, you get here. Alright, and now this is the part that it might not make a whole lot of sense to you. It's kind of like a hand-wavy argument, but so now you have a protonated epoxide, and if you remember, protonated, things, they generally are going to want to go via like an SN1 pathway. So you've protonated your epoxide, and you have water floating around, okay? Because this epoxide is protonated, it's already a good leaving group, right? We don't need a nucleophile to really attack it. And so you can imagine, so I want you to imagine that this is now going to undergo an SN1 pathway. Okay. Right. So if this thing were to undergo an SN1 pathway, then there would be two options. I could either break this bond on the left, and if I broke this bond on the left, then I would get this carbocation and this alcohol. Or I could break the bond on the right. Okay, so let me erase this arrow. If I broke the bond on the right, so if I made this one the leading group, then I would get this carbocation. And hopefully you remember that this carbocation is going to be much more stable, and so this is going to be the preferred pathway. And if this is the preferred pathway, then obviously my water is going to attack the carbocation right there. All right? And therefore, you would expect that you get this product. Okay. And then again, I need to deprotonate this, so whatever my neutral species is, it's not going to be the sulfuric acid, but it would be whatever my nucleophile is probably just going to deprotonate that. Okay. So I get this. Okay. Now I say imagine. So this is the right product that you would get. Okay. However, the reality is that even under acidic / protonated conditions, it actually still follows an SN2 mechanism, which might confuse you. It might confuse you because you might say, okay, well, if it follows an SN2 pathway, why did the water attack the more substituted side? Okay? And the reason for that is because it's a little bit complicated, but basically, even though it follows an SN2 pathway, in the transition state, having the nucleophile attack the more substituted part of that epoxide leads to a more stable transition state, and that transition state is stable enough that it counteracts the steric effects of having to attack a substituted position. All right, so let me give you like an example of sort of what I mean by this. All right, so if I have this epoxide right here, okay, and I have a substituted side and a not as substituted side, right? And I'm going to react this with H2SO4 and an alcohol. So I'm going to react this with, I'll react this with cyclohexanol. All right. Let's talk about the mechanism for what would happen here, and really thinking about the regiochemistry and the types of mechanisms that are going to go on. All right. So I have my epoxide. Okay. So we know that the epoxide is nucleophilic. The first step of this acidic-based mechanism is just going to be protonation of the epoxide. Okay. And then now is when it gets kind of funky. So even though it's protonated, and we know because it's protonated, it's going to, the regiochemistry is going to be similar to the regiochemistry of an SN1 reaction, but it's technically still going to be an SN2 reaction. So it's going to do an SN2 reaction on the tertiary center. Okay. And I know I've said, or hopefully your professor has said multiple times, that you don't do SN2 chemistry on a tertiary center. Epoxides are just a little bit different. Like I said, the strain of this ring is incredibly high, and so this is like a rare case where you are, and you in fact do an SN2 reaction at a tertiary center. So you're going to get that, and again, because it's an SN2 reaction, the stereochemistry changes. So rather than a dash, it's now a wedge. And this is still a wedge, and the OH is over here on it, okay? And again, you're just going to get another one of these molecules to deprotonate that OH for you. Alright? So that would be how you get this product. Right? So hopefully that makes sense. All right. And you can do this with a bunch of other things too. Okay, so if you have an epoxide, you have a tertiary center, right? Instead of H2SO4 and an alcohol, you could think about doing this with like H2SO4 and a thiol. So I'll just do like, thioethanol, right? And it's going to be the same type of thing, right? First step. Okay, your oxygen is nucleophilic, so you're going to protonate that thing. Okay, that gets me to here. Okay, right, and then I have my thiol molecule. Okay. Lone pair on the sulfur, definitely nucleophilic, okay? And because the epoxide is protonated, even though we normally would not do SN2 chemistry here, we're going to do an SN2 reaction, but we're going to do the regiochemistry as if it were an SN1. And so we're going to go there. That's going to go there. And that is going to get me to this guy right here. And then again, the final step is just going to be to deprotonate that hydrogen. Something is going to do that deprotonation. Okay. So that your final product is just the neutral species. Alright? So hopefully that makes sense. Okay. The other thing you can do, if you don't want to use sulfuric acid, you can think about doing this with just a normal, like halogenic acid, right? So if you use HX, so this could be HCl, HBr, or HI. Okay, again, this is going to do the exact same thing, right? So let's imagine this was HBr. Nucleophilic O attacks the electrophilic H. Okay. That gives me a protonated epoxide. Right, again, the protonated epoxide, so it gives me the protonated epoxide, and then I have this Br minus. Okay. Right. So the protonated epoxide, it wants to do, it always is going to do SN2 chemistry, but because it's protonated, it's going to have like the regiochemistry of an SN1 reaction, so the bromide is actually going to go there. That guy is going to go there. Right, and I can't see sorry. My computer keeps freezing. Ugh. I can't remember exactly the way that I drew it before. Alright, well, I think... Hold on. I think I drew it like this, in which case it would be... The product that I'm trying to draw for you guys would be this. So your final product in that case would be this guy. Alright. So that's pretty much all there is to know about the epoxides. I do actually have one little addendum to put. Hopefully it doesn't freak you out too much, but it is probably going to make the regiochemistry of the acidic conditions a little bit more complicated. So just in review, right? So we just did a whole bunch of epoxide reactions, okay? And we talked about the fact that if you are in anionic, otherwise known as basic, or neutral conditions. All right, these ones are the easiest, okay, because the nucleophile will always attack the less substituted, electrophile via an SN2 reaction. Okay, so that one is really easy. And then we talked about the fact that when you're dealing with cationic, otherwise known as acidic conditions, I initially made it probably seem simpler than it really is, and that's because I wanted it to be simpler, but it's actually a little bit more complicated than I initially made it seem, but it's still not that bad, okay? So when you're acidic conditions, it's still ultimately an SN2 reaction, but so there's essentially three different options that you can have. So if the two electrophilic centers are tertiary and primary, or tertiary and secondary, meaning as long as you have a tertiary center on there, okay, the nucleophile will attack the more substituted, and all of the examples I did were examples where it was a tertiary and a primary, or a tertiary and a secondary. The nucleophile will attack the more substituted position, which for an SN2 reaction is the opposite of what you would expect, but it's because the transition state is so stabilized as you release that strain that it essentially handles the steric constraints of doing an SN2 at a tertiary center. So the nucleophile will attack the more substituted electrophile. However, and I didn't mention this, but even if you're under cationic or acidic conditions, if you don't have a tertiary center and you only have a primary and a secondary center, then it actually behaves like an SN2 reaction and it will attack the primary, even under acidic conditions. All right, and so I'll give you an example of that. So like we talked about the fact that like if I have this epoxide, right, and if I have like a tertiary center and I use if I use H2SO4, well actually, I won't use H2SO4. If I use like HBr, right? We talked about the fact that the bromine is going to attack the more substituted position. And so the final product is actually going to be this, right? Okay. However, even under acidic conditions, if I didn't actually have a tertiary center at all, and I was just dealing with like a secondary versus a primary, then the bromine would actually just attack the primary like it would if it were an anionic or neutral condition. So I know that's kind of shitty. And if you really, I feel bad because I feel like I'm not really explaining it that well, because these videos are already like really, really, really long, and I don't want to make them longer. But if you come to the review, I will gladly take time to really get into, like why are we allowed to do SN2 on a tertiary center, and why, even under cationic conditions, if it's if it's primary versus secondary, it'll still go primary. It seems like it's just sort of doing what it wants to do at that point. But there is a logic behind it, and I don't want to get into it because it would be a lot for me to explain it. But if you're confused about that, and you want to know sort of why these rules are a thing, ask me about it, and I'll describe it to you. Okay? But those are the rules. Okay? So again, epoxides, the mechanism I think is pretty simple and straightforward. The main thing that you have to get good at is understanding the regiochemistry, right? It's understanding where the nucleophile is going to attack, okay? It always, regardless, it's always going to be an SN2, meaning whenever the nucleophile attacks, you always have to switch the stereochemistry, so wedges become dashes, dashes become wedges, okay? However, if it's anionic or basic, the nucleophile is always going to attack the least substituted electrophilic carbon. If it's cationic or acidic, it's always going to attack the most substituted carbon unless none of the carbons are primary unless none of the carbons are tertiary. And if none of the carbons are tertiary, then it's just going to do the same thing that it would have done if it was anionic, which is just attack the primary position, attack the less substituted position. All right. So hopefully that makes sense. That's all I got for epoxides. I don't think I'm missing anything on the epoxides. Like I said, I think at this point we talked about most of the reactions that you can do with them. As always, ask me questions if you are watching this video and I said something that didn't really resonate with you, or I said something that sounded confusing to you, or if maybe my voice got jumbled and you couldn't hear me that well. But I hope you have a great day, and I will see some of you guys tomorrow for the review.